In this lecture, we'll answer two questions. On both questions, we'll find out the area of a shaded region. So we'll start with the first question. In the drawing, we have the big quarter circle AOB. We know that AO equals to 10 units in its length. AO is the radius of this big quarter circle AOB. Likewise, BO is also the radius of this big quarter circle AOB, therefore it is equal to 10 units in its length, according to what is given as the question. Inside the big quarter circle AOB, we have this semicircle and this small quarter circle. So we define the center of this semicircle. This point is point C. BO is the radius of this big quarter circle AOB, but BO is also the diameter of this semicircle. So we know that the diameter BO of this semicircle equals to 10, and therefore the radius CB must be equal to 5, and the radius CO of this semicircle must be also equal to 5 units in its length. It is half the diameter BO. In the next step, we define the touching point of this small quarter circle with this big quarter circle. This point is point P. We define this point as point Q. We define this point as point S. We will define the touching point of this big semicircle with this small quarter circle. This point is point M. Repeat again. Point M is the touching point of this small quarter circle with this big semicircle. So those two shapes touch each other externally at point M. That is to say, this is the small quarter circle that touches this big semicircle at point M. And externally at point M. And whenever you have an external line between two shapes, you can implement rule 10. So repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together passes through their touching point. So in the drawing, you have those two circles that touch each other externally at this point, point P. This is point O, that is the center of this circle. This is point M, that is the center of this circle. The straight line that connects the centers together is, of course, the straight line OM. And this straight line OM, according to rule 10, must pass through point P, that is their touching point. Or the straight line OM must pass through their touching point, that is point P. Or in other words, OPM is one straight line. OPM is one straight line according to this rule, rule 10. If OPM is one straight line, it means that OM in total must be equal to OP plus PM. So you can actually implement rule 10 in our drawing. In our drawing, this is the small quarter circle that touches externally this big semicircle at point M. The center of this small quarter circle is there at point Q. The center of this big semicircle is there at point C. The straight line that connects the centers together is, of course, the straight line CQ. And according to rule 10, the straight line CQ must pass through point M, that is their touching point. Again, the straight line CQ must pass through their touching point, that is point M. Or in other words, CMQ is one straight line. So we will join point CMQ together by a straight line. And according to rule 10, the straight line CQ must pass through point M, that is their touching point. So it is very easy to see from the drawing that the straight line CQ indeed passes through point M, that is their touching point, exactly like rule 10. And because of the fact that CMQ is one straight line, it means that CQ in total must be equal to CM plus MQ. That is to say, CQ in total equals to CM. CM is the radius of this semicircle, that equals to 5. plus MQ. What is the definition of MQ? Line segment MQ starts from point Q, that is the center of this quarter circle, and ends at point M, that is the point on the quarter circle itself. So this is exactly the definition of a radius. Therefore, QM is the radius of this small quarter circle, PQS. So we define the radius of this small quarter circle PQS as x. So QM equals to x. And according to rule 10, CQ in total equals to CM, that is 5, plus MQ, that is x. So in total, CQ equals to x plus 5 units in its length. So CQ equals to x plus 5. AOB is a quarter circle, and therefore this is a right angle. Likewise, PQS is also a quarter circle, and therefore this is also a right angle. In the next step, I'll copy the right triangle COQ, this right triangle COQ in a new page. We will implement the Pythagoras theorem on this right triangle, triangle COQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side CO of this right triangle COQ equals to 5 units in itself. It is actually the radius of the semicircle. And we just right now found out that the hypotenuse CQ equals to x plus 5 units in its length, according to rule 10. Here by PT is the evaluation of Pythagoras theorem. So actually, this is the right triangle COQ. It according to the original drawing. In this right triangle COQ, according to the Pythagoras theorem, CQ squared, that is the square of the hypotenuse, equals to CO squared plus OQ squared. So I write it down. CQ squared, that is the square of the hypotenuse, is equal to CO squared plus QO squared. CQ is x plus 5, therefore CQ squared is x plus 5 squared. And it is equal to CO squared. CO is 5, therefore CO squared is 5 squared, that is 25. Plus QO squared. QO is the missing sign, so we have to see this. So it is QO squared. So here we will subtract 25 from this equation 1. And you get that according to equation 1, QO squared equals to x plus 5 squared minus 25. Okay, again, according to equation 1, we found out that QO squared equals to x plus 5 squared minus 25. In the next step, we will join points O and P together by straight line. Point O is the center of this big quarter circle AOB. Point P is the point of the big quarter circle. Therefore, OP is the radius of the quarter circle. It equals to 10 units in its length according to what is given as the question. So PO equals to 10. What is the definition? Plan 7 QP. Plan 7 QP starts from point Q, that is the center of this quarter circle, small quarter circle PQS, and ends at point P, that is the point of the quarter circle itself, the small quarter circle itself. Therefore, QP is the radius of this small quarter circle PQS, and therefore it is equals to x units in its length. So PQ equals to x. So in the next step, I'll copy this right triangle PQO in a new page, and we will implement the Pythagoras theorem on this right triangle PQO. Here by PT is the abbreviation for Pythagoras theorem. So the hypotenuse PO of this right triangle PQO equals to 10 units in its length. It is the radius of the big quarter circle AOB. So actually, this is the right triangle PQO, that is the curve from the original drawing. In this right triangle PQO, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. So I write it down. This will be equation 2. According to equation 2, PO squared, that is the square of the hypotenuse, is equal to PQ squared plus QO squared. PO is 10, therefore PO squared is 10 squared, that is 100. And it is equals to PQ squared. PQ is x, therefore PQ squared is x squared. Plus QO squared. QO is the missing side, so we leave it as it is. Here we will subtract x squared from this equation 2. We get, according to this equation 2, QO squared equals to 100 minus x squared. And again, according to equation 2, we found out that QO squared equals to 100 minus x squared. This is according to equation 2, while according to equation 1, we have only found out that QO squared equals to x plus 5 squared minus 25. So now, according to equation 1, we have only found out that QO squared equals to x plus 5 squared minus 25. So actually have two different equations for q all square. According to equation 1, q all square equals to 100 minus x square, while according to equation 2, q all square equals to x plus 5 square minus 25. Therefore, we will create equation 3 that states that q all square according to equation 1 must be equal to q all square according to equation 2. And again, according to equation 3, q all square according to equation 1 must be equal to q all square according to equation 2. So q all square according to equation 1 equals to 100 minus x square, and it must be equal to q all square according to equation 2. q all square according to equation 2 equals to x plus 5 square minus 25. So in total, according to equation 3, we actually found out that 100 minus x square equals to x plus 5 square minus 25. So according to equation 3, 100 minus x square equals to, here we have x plus 5 square, so we'll open the brackets of this expression, and we get that x plus 5 square equals to x square plus 5 square, that is 25, plus 2 times x times 5, that is plus 10x minus 25. So in this side of the equation 3 we have 25 minus 25 is 0. So in total we found out that according to equation 3, 100 minus x squared equals to x squared plus 10x. Here we let x squared to this equation 3. Again, according to equation 3, x squared plus x squared is 2x squared plus 10x equals to 100. And again, according to equation 3, we found out that 2x squared plus 10x, of course, equals to 100. Here we will subtract 100 from this equation 3, and finally get that according to equation 3, 2x squared plus 10x minus 100 equals to 0. Here we will divide this equation 3 by 2. Again, according to equation 3, x squared over 2 is x squared, and 10x over 2 is 5x, and minus 100 over 2 is minus 50 equals to 0 over 2. 0 over 2 is 0. So in total we found out that according to equation 3, x squared plus 5x minus 50 equals to 0. So this is a quadratic equation. And the general formula for a quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say, x squared plus 5x minus 50 equals to 0. The variable that we are looking for is x. X, it is actually the radius of this small quarter circle PQS. So looking for the value of this radius of this small quarter circle PQS. So X is the radius of this small quarter circle PQS. And the coefficient A of our specific quadratic equation equals to 1. The coefficient B equals to 5. And the coefficient C equals to minus 50. The only thing that is left to do is to put the data of our specific quadratic equation, this data, on this formula for X. And this formula for X. In this way, we'll find out the value of the values of X. Again, X is the radius of the small quarter circle PQS. So we'll do it now and get that X equals to minus B. B is 5, so minus B is minus 5. Plus minus square root of B squared. Again, B is 5, so B squared is 5 squared, that is 25. Minus 4 times A times C. So this is minus 4 times A. A is 1, so minus 4 times 1 is minus 4 times C. C is minus 50, so minus 4 times minus 50 is plus 200. So in total, minus 4 times A times C is plus 200. So in total, inside the root we have 25 plus 200 divided by 2A. A is 1, so 2A is 2 times 1, that is 2. So in total, we found out that X equals to minus 5 plus minus square root of 25 plus 200 over 2. So X equals to minus 5 plus minus 25 plus 200 is 225. So inside the root we left only with 225 over 2. So in total we found out that X equals to minus 5 plus minus the square root of 225 is 15 over 2. So here we have two solutions that are possible for X. The first solution for X is that X equals to minus 5 minus 15 over 2. Minus 5 minus 15 is minus 20, and minus 20 over 2 is minus 10. So according to the first solution for X, X equals to minus 10. X can never be equal to minus 10, because X is the length of this radius of this small quarter circle PQS. So X is a length, it must be a positive number. But 10 is a negative number. So this solution is a correct solution, so we'll cancel this solution and we'll take into account on the second solution for X. The second solution for X is that X equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10, over 10 over 2 is 5. So the second solution for X is that X equals to 5 units in its length. Again, we found out that the radius X of this small quarter circle PQS is equal to 5 units in its length. Our task is to find out the area of this shaded region. So what is the area of this shaded region? From the drawing, it is very easy to see that the area of this shaded region in total must be equal to the area of the big quarter circle AOB. It is equal to the area of the big quarter circle AOB minus the area of this semicircle minus the area of this small quarter circle PQS. Repeat again, we found out that the area of this shaded region in total it is equals to the area of the big quarter circle AOB minus the area of this semicircle minus the area of this small quarter circle PQS. Actually, it is very easy to see from the drawing that if you remove from the area of this big quarter circle AOB the area of this semicircle and the area of this small quarter circle PQS, what is left is actually the area of this shaded region. And therefore, the area of the shaded region in total must be equal to the area of the big quarter circle AOB minus the area of the semicircle minus the area of the small quarter circle PQS. What is the area of the big quarter circle AOB? The area of the big quarter circle AOB, because of the fact that the radius of this big quarter circle is 10, therefore the area must be equal to pi times 10 square over 2. So the area of the big quarter circle AOB must be equal to pi times the radius squared, that is 10 square over 2. Minus the area of this semicircle. The radius of this semicircle is 5, and therefore the area of this semicircle must be equal to pi times 5 square over 2. So in total, the area of the semicircle must be equal to pi times the radius squared, that is 5 square over 2. Actually, the area of the big quarter circle is pi times the radius squared over 4. Okay? It is pi times the radius squared, that is 10 square over 4. Because it is a quarter circle, we have to divide the circle into 4. The quarter circle is 1/4 of the circle itself. Therefore, we have to divide the area of the circle itself, that is pi 10 square by 4. So it is pi times 10 square over 4. That is the area of the big quarter circle AOB. Minus the area of the semicircle is equals to pi times the radius of the semicircle, that is 5 squared over 2. Minus the area of this small quarter circle PQS. We already found out that the radius of this small quarter circle PQS x is equal to 5, and therefore the area of this small quarter circle PQS must be equal to pi times the radius squared, that is 5 square over 4. So in total, the area of the small quarter circle PQS must be equal to pi times the radius squared, that is 5 square over 4. Ten square is 100, so in the numerator of this expression we have 100 pi over 4 minus, in the numerator of this expression we have 25 pi over 2. In order to overcome factor with the other two expressions, we will multiply both the numerator and the denominator of this expression by 2. So 25 pi minus 25 pi times 2 is minus 50 pi over 2 times 2 is 4. We have here in the numerator 25 pi over 4. 25 pi over 4. So here we take 4 as a common factor out of those three expressions. And the numerator we have 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi. So in total we found out that the area that we are looking for in this question, that is the area of this shaded region, it is equal to either 25 pi over 4 square units in size, or in terms of numbers it is equal to 19.635 square units in size. Repeat again, we found out that the area that we are looking for this question, that is the area of this shaded region, it is equal to either 25 pi over 4 square units in size, or in terms of numbers it is equal to 19.635 square units in size. So we finished to answer the first question. In the next step, I'll present to the second question and resolve the second question of this lecture. In the second question, our task is to find out the area of this shaded region. So in the drawing we have two semicircles that intersect with each other at those 2 points. We know that the diameter AB of this semicircle equals to 5. When we find the radius of this semicircle, this point is 0.0. If the diameter AB of this semicircle equals to 5, it means that the radius of B must be equal to 5 over 2, or 5 halves. Likewise, the radius OA of this semicircle AB must be also equal to 5 half units in its length. This is half of the diameter AB, that is 5. In the next step, we will divide this drawing into 3 parts. We define the size of this shaded area as A. That is to say, the shaded area equals to A square units in size according to our definition. We define the intersection point between BC and this semicircle AB. This point is point M. So we will define the size of this shape MB as B. That is to say, this shape that is actually a small semicircle, it is equal to B square root in size according to our definition. Likewise, we define the size of this shape MAB, as C. That is to say, shape MAB equals to C square root in size according to our definition. Repeat again, the size of this shaded area, that is the area that we are looking for, is equals to A square root in size. The size of this area, this is a semicircle, is equals to B square root in size, and finally the size of this shape A and B, it is equals to C square root in size according to our definition. It has given us the question that those two semicircles can go into each other. That is to say, this is semicircle AB that can go into this semicircle CB. And because of the fact that those two semicircles can go into each other, they must have also the same areas. That is to say, the area of this semicircle AB is equal to the area of this semicircle CB. So I write it down. Repeat again, because of the fact that those two semicircles can go into each other, they must have also the same areas. That is to say, the area of semicircle AB must be equal to the area of semicircle CB. But what is the area of this semicircle AB? Semicircle AB consists of those two shapes. And therefore, the area of semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. The area of this shape A and B is C, the area of this ladder shape is B. So in total, the sum of those two shapes that semicircle AB consists of is equal to B plus C. So in total, the area of semicircle B plus C equals the area of semicircle AB equals to B plus C square root in size. And it is equals to the area of semicircle CB. What is the area of this semicircle? CB. Semicircle CB consists of those two shapes. And therefore, the area of semicircle CB must be equal to the sum of the areas of those two shapes that is consists of. That is to say that the area of semicircle CB in total must be equal to A plus B. So the area of semicircle CB equals to A plus B. So according to equation 1, we actually found out that B plus C equals to A plus B. Here we will subtract B from this equation 1, and finding that according to equation 1, here B will get cancelled, and B also gets cancelled. So according to equation 1, we actually found out that C equals to A. This is to say, the area of this shaded region is equals to A square root in size is equal to the area of this shape A and B is equals to C square root in size. So those areas have the same size. We are looking for the area of this shaded region. So we just find out the area of this shape A and B is equals to C square root in size. And because of the fact that C equals to A, it means that the area of this shape A and B is also equal to the area of this shaded region CB. So our mission is to find out the area of this shape A and B. And because of the fact that C equals to A, it means that the area of this shape A and B is equal to the area of this shaded region, that is the shaded region that we are looking for in this question. Okay. In the next step, we will do a construction. This is to say, from point M, we will do perpendicular on AB. Again, from point M, we will do perpendicular on the diameter AB of this semicircle. So actually, this angle equals to 90 degrees in size, and this angle also equals to 90 degrees in size according to our construction. We will define the touching point of the perpendicular from point M and AB. This point is point Z. We will define the length of perpendicular MZ as h. That is to say, perpendicular MZ equals to h units in its length according to our definition. In the next step, we will join points A and M together by a straight line. By joining points A and M, we get that peripheral A and B. This is peripheral A and B. Peripheral A and B subtend on chord AB, that is the diameter of this semicircle. And according to rule 7, any peripheral that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. So I'll repeat quickly on rule 7. According to rule 7, if a peripheral subtend on the diameter of the circle or semicircle, then it is equal to 90 degrees in its size. In the moment we have a circle. This is peripheral ACB that subtend on chord AB, that is the diameter of this circle, and therefore according to this rule 7, peripheral ACB must be equal to 90 degrees in its size. So according to rule 7, any peripheral that subtend on the diameter of a circle or semicircle must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. Why? Because in our drawing we have peripheral angle A and B. This is peripheral angle A and B that subtend on A and B, that is the diameter of the semicircle, and therefore it must be equal to 90 degrees in its size according to rule 7. So peripheral angle A and B equals to 90 degrees in its size according to rule 7. In the next step, we'll focus on this right triangle, triangle A and B. So I'll copy the right triangle A and B in a new page. We'll analyze this right triangle, triangle A and B. We know that AB, this is one side of this right triangle A and B, is equals to 5 units in its length. So actually, this is the right triangle A and B that are coming from the original drawing. Repeat again that AB equals to 5 units in its length. MZ is the height to the base AB. Why MZ is the height to the base? Because it's right 90 degrees with the base. Those two angles are both right angles. So in the next step, we'll find out the area of this right triangle A and B by using two different methods, and then we'll create equation 1 that said that the area of triangle ABC according to the first method of calculation must be equal to the area of this right triangle AB according to the second method of calculation. So according to the first method of calculation, the area of this triangle A and B is equal to the base AB times the height to the base, that is h, over 2. And in the next step, we'll find out the area of this triangle A and B according to the second method. The area of this triangle A and B according to the second method of calculation, it is equal to the base AM times the height MB over 2. So equation 1 states that the area of triangle A and B according to the first method of calculation must be equal to the area of triangle A and B according to the second method of calculation. AB is 5. So here we have 2 on both sides of this equation 1, so 2 will get cancelled. And then we have to only with AB times h, AB times h equals to AM times MB. AB equals to 5, therefore we solve AB in this equation 1 by 5. So in this side of the equation we have 5h equals to AM times MB. And again, according to equation 1, we found out that 5h equals to AM times MB. I'll copy this right triangle A and B in the new page, and we will continue to analyze this right triangle, triangle A and B. Especially, this is the right triangle A and B. In the comments from the original drawing, in this right triangle A and B, sinus 15 degrees is equal to AM over AB. So sinus 15 degrees equals to AM over AB. AB is 5, so in total we found out that sinus 15 degrees equals to AM over 5. Here we will multiply this equation by 5 and finally we get that AM equals to 5 times sinus 15 degrees. So in this right triangle A and B, cosine 15 degrees equals to MB over AB. So this equals to MB over AB. AB is 5. So in total, we found out that cosine 15 degrees equals to MB over 5. Here we will multiply this equation by 5 and finally we get that MB equals to 5 times cosine 15 degrees while AM, we found out that AM equals to 5 times sinus 15 degrees. Now we return to equation 1. So we found out the values of AM and MB. According to equation 1, 5H equals to AM plus MB. So we substitute AM in this equation 1 by 5 times sinus 15 degrees and substitute MB in this equation 1 by 5 times cosine 15 degrees. We do it now, we get that according to equation 1, 5H equals to AM. AM is 5 times sinus 15 degrees times MB. MB is 5 times cosine 15 degrees. So in total, we found out that according to equation 1, five H equals to 5 times sinus 15 degrees times 5 times cosine 15 degrees. Here we will divide this equation 1 by 5 and finally get that according to equation 1, 5H over 5 is 8 and it is equals to, here we have 5 times 5 is 25 and 25 over 5 is 5. So we have to find 5 in this side of equation 1. So it is equals to 5 times sinus 15 degrees times cosine 15 degrees. So if it again, so in total, according to equation 1, we found out that H, that is the I to the base AB, MZ is equals to H, that is the I to the base to the side AB. It is equal in total to 5 times sinus 15 degrees times cosine 15 degrees. Here we use the trigonometric identity that states that sinus 2A is equal to 2 times sinus A times cosine A. So according to this trigonometric identity, sinus 2A equals to 2 sine A cosine A. Here we will divide this trigonometric identity by 2. And finding out that according to this trigonometric identity, sinus 2a over 2 equals to sinus a times cosine a. We use this trigonometric identity that says that sinus 2a over a equals to sinus a times cosine a in order to find out the value of sinus 15 degrees times cosine 15 degrees. So according to equation 1, we actually found out that a equals to 5 times sinus 15 degrees times cosine 15 degrees. According to this trigonometric identity, sinus a times cosine a equals to sinus 2a over 2. And therefore, sinus 15 degrees times cosine 15 degrees will be equal to sinus 2 times 15 degrees, that is 30 degrees, over 2. So in total, we found out that sinus 15 degrees times cosine 15 degrees, according to this trigonometric identity, equals to sinus 30 degrees over 2. So in total, according to equation 1, we found out that h equals to 5 times sinus 30 degrees over 2. So in total, according to equation 1, we actually found out that h equals to 5 over 2 times sinus 30 degrees. Sinus 30 degrees is 1/2. So in total, we found out that h equals to 5 times 1, that is 5, over 2 times 2, that is 4. So in total, we found out that according to equation 1, h equals to 5/4 units in its length. So the perpendicular MZ is equals to h is equal to 5 square units, 5 square units inside, 5 quarters is equals to 5 quarters units in its length. Our task is to find out the size of this shaded region. We already found out that A equals to C. That is to say, the area of this shaded region equals to the area of this shape A and B. And because of the fact that those two areas are equal to each other, in order to find out the size of this shaded area, we just have to find out the area of this shape A and B. Because of the fact that those two areas are equal to each other, the size of this shaded area equals to the size of this shape A and B. So, first of all, we'll join points O and M together by straight line. By joining points O and M, we get a side angle AOM. This is side angle AOM. Side angle AOM subtend on chord MA. Again, side angle AOM subtend on chord MA. Likewise, we have peripheral angle ABM. This is peripheral angle ABM that subtend on the same chord called AM. Peripheral angle ABM equals to 15 degrees inside according to what is given in the equation. And because of the fact that those two angles are both subtend on the same chord called AM, the size of this center angle AOM must be twice as large as the size of this peripheral angle ABM. The size of this peripheral angle ABM is 15, and therefore the size of this center angle AOM that subtend on the same chord called AM must be equal to 15 degrees times 2, that is 30 degrees. Therefore, according to rule 13, the size of this center angle must be equal to 30 degrees in its size. Repeat quickly on rule 13. According to rule 13, a center angle is twice as large as the peripheral angle subtended on the same chord. In the drawing we have a circle. This is peripheral angle ACB. This is equals to 30 degrees in its size, and it's subtend on chord AB. Again, peripheral angle ACB subtend on chord AB. This is equals to 30 degrees in its size. Likewise, this is angle AOB that subtend on the same chord called AB. And because of the fact that those two angles are both subtend on the same chord called AB, the size of this angle AOB must be twice as large as the size of this center triangle ACB because they are both subtend on the same chord called AB. And because of the fact that the size of this triangle ACB equals to theta, then the size of this triangle must be equal to theta. So if we have two angles that are both subtend on the same chord, in this case it is called AB, the size of the side triangle must be twice as large as the size of this triangle that subtend on the same chord called AB. The size of this triangle ACB is theta, and therefore the size of this side triangle AOB must be equal to theta. So we already implemented all 13 in our drawing, as I mentioned before here. Those two angles are both subtend on the same chord called MA. The size of this triangle ABM is 15 degrees, and therefore the size of this triangle AOM that subtend on the same chord called AM must be equal to 15 degrees times 2, that is 30 degrees according to rule 13. So, as I already mentioned before, those two shapes are equal to each other in their sizes. This is to say, A equals to C, or this is the area of this shaded region is equal to the area of this shape AMB. So in order to find out the size of this shaded area, we just have to find out the size of this shape A and B, because they are equal to each other and their sizes, because A equals to C. So what is the size of this shape A and B? Shape A and B consists of two smaller shapes. The first shape the big shape A and B consists of is this sector AMO, and the second shape that this big shape A and B consists of, this is triangle AMOB. Therefore, the sum of the areas of those two shapes is equal in total to the area of this big shape A and B, and those two shapes are equal to each other in their sizes, and therefore the size of this shape A and B is equal to the size of this shaded area, because A equals to C. So this is sector AOB. What is a sector? A sector is a portion of a circle enclosed by two radii and the arc AB and the arc, in this case it is arc AM between them. But again, on the definition of a sector, the green shape AOB is a sector. It is a portion of this circle enclosed by two radii and arc AB between them. So a sector, it is like a slice of a pizza. The two radii of this sector are defined as the legs of the sector. So the area of this sector AOB, the green shape AOB, in total it is equal to the area of the circle that contains the sector, that is pi r square. R is the radius of the circle, times the angle between the legs of the sector, that is theta, or 360 degrees. Repeat again. A sector is a portion of a circle enclosed by two radii and arc AB between them. And the area of this sector equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. So the area of the sector AOB in total equals to pi r squared times theta over 360 degrees. Repeat again, note that those two shapes are equal to each other in their sizes. So in order to find out the size of the shaded area, we just have to find out the size of this big shape A and B. But this big shape A and B consists of those two smaller shapes. The first shape that it consists of is this sector AMO, and the second shape that it consists of is this is triangle MOB. And therefore the area of this big shape A and B must be equal to the sum of the areas of those two shapes that it consists of, and this is also equal to the area of this shaded region. That is the area that we are looking for this question, because A equals to C. So write it down. If we found out that the size of the shaded area in total, it is equal to this is the shaded region is equal to the size of this shape A and B. But this shape A and B consists of two smaller shapes. It consists of this sector AMO so it is there the first shape that is consists of this sector AMO. The rounded line above AMO is the sign of a sector. It means sector AMO in total. This expression means the area of sector AMO. That is the first shape that the big shape AMB consists of. The second shape that the big shape AMB consists of. This is a triangle MOB. That's the second shape that the big shape AMB consists of. It's actually triangle MOB. So, what is the area of this sector AMO according to the formula that I presented to you a couple of minutes ago? The area of sector AMO must be equal to pi r squared. That is the area of the circle that contains the sector. R is the radius of this semicircle. Pi r squared times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Plus the area of the second shape, that is the big shape A and B consists of, is actually this shape, that is triangle MOB. So this plus the area of this triangle MOB. What is the area of this triangle MOB? We'll choose the base as BO. BO is the radius of this semicircle. This is 5/4. So the base is BO times the height to the base is h. Why the height to the base is h? Because it's greater than 90 degrees with the extended base BO. The extended BO is here. And it's greater than 90 degrees with the extended BO. Those two angles are both right angles. So the height to the base BO is h over 2. So in total, the area of this triangle MOB equals to the base BO times the height to the base, that is h, over 2. So it is BO times h over 2. R is 5/4, 5 halves, and therefore r squared is 5 halves squared. So pi r squared is pi times 5 halves squared. Pi times 5 halves squared. 30 degrees over 360 degrees is 1 over 12. So in total, if you want to know that the area of sector AMO equals to pi times 5 over 2 squared over 12. And we have here plus the area of this triangle MOB. BO is 5 halves times h. S is h 5, h equals to 5/4 over 2. You have to divide it by 2. So in total, if you found out that the area of the shaded region equals to pi times 5 over 2 squared. 5 over 2 squared equals to 5 squared, that is 25, over 2 squared, that is 4. So in total, this expression equals to 25 pi over 4, and we have to divide it also by 12. Plus, here we have 5 times 5 is 25, and we have 2 times 2 is 4, and 4 times 4 is 16. So in total, the area of triangle MOB equals to 25 over 16 squared in size. And here we have in the numerator 25 pi over 4 times 12 is 48, plus 25 over 16. So in total, if you want to know that the area of the shaded region equals to either 25 pi over 48 plus 25 over 16, or in terms of numbers, it is equal to 3.2 squared in size. And again, I should found out that the area that we're looking for in this question, that is the area of this shaded region, in total it is equal to 3.2 squared in size. So we finish the answer on the second question. In the next step, I will start the lecture. I will start with the first question, of course. In the first question, our task was to find out the area of this shaded region. So in the drawing, we have the big quarter circle AOB. Inside this big quarter circle AOB, we have this semicircle and this small quarter circle PQS. Those two shapes touch each other externally at this point, point M. We know that AO, that is the radius of this big quarter circle AOB, equals to 10. Therefore, BO is also the radius of this big quarter circle AOB, therefore it is equals also to 10. We define the center of this semicircle, this point is point C. The diameter BO of the semicircle is 10, therefore the radius CB must be equal to 10 over 2 to the 5. Likewise, the radius CO must be also equal to half of the diameter, that is 5. AOB is a quarter circle, and therefore this is a right angle. Likewise, PQS is also a quarter circle, and therefore this is a right angle. Those two shapes, that is to say, this is the small quarter circle PQS, touch each other externally, touch this semicircle externally at point M. So those two shapes have an external between them at point M, and therefore we can implement the rule 10. Rule 10, according to rule 10, if two circles touch each other externally, then the straight line that connects the centers together passes through their touching point. In the drawing, we have those two circles that touch each other externally at point P. The center of this circle is at point O. The center of this circle is at point M. The straight line that connects the centers together is, of course, the straight line OM. And this straight line OM must pass through their touching point, that is point P. So the straight line OM must pass through point P, that is their touching point. Or OPM is one straight line. Again, according to this rule, rule 10, OPM is one straight line. If OPM is one straight line, it means that OM in total must be equal to OP plus PM. So we can implement rule 10 in our drawing. Well, because in our drawing, this is the semicircle that touch externally this small quarter circle PQS at point M. The center of this small quarter circle is at point Q. The center of this big semicircle is at point C. The straight line that connects the centers together is, of course, the straight line CQ. And the straight line CQ must pass through their touching point, that is point M. Or CMQ is one straight line. If CMQ is one straight line, it means that CQ in total must be equal to CM, that is the radius of this semicircle, that is 5, plus MQ, that is equals to X, according to our definition. MQ is the radius of this small quarter circle, PQS. And therefore it is equal to X units in step, according to our definition. So in total, CQ must be equal to X plus 5, according to rule 10, because CQM is one straight line. CMQ is one straight line. So in total, we can find out that CQ equals to X plus 5 units in its time. In the next step, I copied the right angle CQO in a new page and implemented the Pythagoras theorem on this right angle CQO. According to the Pythagoras theorem, in a right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right angle CQO that I copied from the original drawing. CQ is the hypotenuse of this right angle, that is equals to X plus 5 units in itself, according to rule 10. CO is the radius of this semicircle, that is equals to 5. And QO is the missing side. So according to the Pythagoras theorem, this right angle CQ squared, that is the square of the hypotenuse, equals to CO squared plus QO squared. CQ is X plus 5, therefore CQ squared is X plus 5 squared. This equals to CO squared. CO is 5, therefore CO squared is 5 squared, that is 25. Plus QO squared. QO squared is the missing side, so we limit this. So in total, according to equation 1, we can find out that X plus 5 squared equals to 25 plus QO squared. Here we subtract 25 from this equation, equation 1, we can find out that according to equation 1, QO squared equals to X plus 5 squared minus 25. In the next step, we join points O and P together by straight line. What is the definition of line segment OP? Line segment OP starts from the center of the big quarter circle, that is to say from point O, and ends at point P, that is the point of the big quarter circle itself. So this is exactly the definition of a radius. So OP is the radius of this big quarter circle, that is equals to 8 units in itself, according to what is given as the question. So this is a right angle because PQS is the quarter circle. So in the next step, I copied the right angle PQO in a new page and implemented the Pythagoras theorem on this right angle PQO. What is the definition of line segment QP? Line segment QP starts from the center of this form, quarter circle, that is point Q, and that's in point P, that is a point on the small quarter circle itself. So this is exactly the definition of radius. Therefore, QP is the radius of this small quarter circle, that is equals to x. So in the next step, we're calling the right angle PQO in a new page, and we implemented the Pythagoras theorem on this right angle PQO. This is the right angle PQO that are going from the original domain. This right angle PQO, PO squared, that is the square of the hypotenuse, equals to PQ squared plus QO squared. PO is 10, therefore PO squared is 10 squared, that is 100, and this equals to PQ squared. PQ is x, therefore PQ squared is x squared plus QO squared. QO squared is the missing sign, so we need to see this. So in total, according to equation 2, if you found out that 100 equals to x squared plus QO squared. Here we subtract x squared from this equation 2, and finally found out that according to equation 2, QO squared equals to 100 minus x squared. This is according to equation 2, while according to equation 1, we already found out that QO squared equals to x plus 5 squared minus 25. So we have two different equations for QO squared. Therefore, we created equation 3 that says that QO squared according to equation 1 must be equal to QO squared according to equation 2. QO squared according to equation 1 equals to 100 minus x squared. It must be equal to QO squared according to equation 2. When QO squared according to equation 2 equals to 100 minus x squared. So in total, we found out that 100 minus x squared equals to x plus 5 squared minus 25. Again, here QO squared according to equation 1 equals to x plus 5 squared minus 25. It must be equal to QO squared according to equation 2, that equals to 100 minus x squared. So in total, according to equation 3, we found out that 100 minus x squared equals to x plus 5 squared minus 25. So here, according to equation 3, we found out that 100 minus x squared equals to x plus 5 squared. Here we open the brackets of this expression and finally found out that according x plus 5 squared equals to x squared plus 5 squared, that is 25, plus 2 times x times 5, that is 10x, minus 25. So in this equation 3, we have 25 minus 25, that is all. After we cancel 25, we left only with x squared plus 10x, that equals to 100 minus x squared. So in total, according to equation 3, we found out that 100 minus x squared equals to x squared plus 10x. Here we added x squared to this equation, equation 3, and found out that according to this equation 3, x squared plus x squared is 2x squared, plus 10x equals to 100. Here we subtracted 100 from this equation 3, and found out that according to this equation 3, 2 times x squared plus 10x minus 100 equals to 0. Here we divided this equation 3 by 2, and found out that 2x squared over 2 is x squared, plus 10x over 2 is 5x, and minus 100 over 2 is 50, and it equals to 0 over 2 is 0. So in total, we found out that according to equation 3, x squared plus 5x minus 50 equals to 0. This is the quadratic equation, and the general formula for quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the value that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus 4 of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say, x squared plus 5x minus 50 equals to 0, the variable that you are looking for is x. Here, x is the radius of this small quarter circle PQS. The coefficient a equals to 1, the coefficient b equals to 5, and the coefficient c equals to minus 50. The only thing that is left to do is to put the data of this specific quadratic equation inside the general formula for x, and this way we find out the value of the values of x. This is the radius of this small quarter circle PQS. We did it, and we found out that x equals to minus b. B is 5, so minus b is minus 5, plus minus square root of b squared. B is 5, so b squared is 5 squared, that is 25. Minus 4 times a times c. So it is minus 4 times a. A is 1, so minus 4 times 1 is minus 4 times c. C is minus 50, so minus 4 times minus 50 is plus 200. So inside the root we left only with 25 plus 200 over 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we found out that x equals to minus 5 plus minus 25 plus 200 is 225 over 2. So we found out that x equals to minus 5 plus minus, the square root of 225 is 15 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 5 minus 15 over 2. Minus 5 minus 15 is minus 20, and minus 20 over 2 is minus 10. So according to the first solution for x is equals to minus 10 units x length. And because of the fact that x is the length, it is the length of this radius PQS, of this quarter circle PQS. X as a length, it must be a positive number. Minus 10 is a negative number, so this solution is the correct solution. So we take into account only the second solution for x. The second solution for x is x equals to minus 5 plus 15 over 2. Minus 5 plus 15 is 10, and 10 over 2 is 5. So the second solution for x, that is to say the radius of this small quarter circle PQS equals to x, and x equals to 5 units in its length. So x equals to 5. Our task is to find out the size of this shaded region, or the area of this shaded region. What is the area of this shaded region? From the drawing it is very easy to see that the area of the shaded region in total must be equal to the area of the big quarter circle AOB minus the area of this semicircle minus the area of this small quarter circle PQS. Repeat again, the area of the shaded region in total must be equal to the area of the big quarter circle AOB minus the area of the semicircle minus the area of the small quarter circle PQS. It's very easy to see from the drawing that if you remove from this big quarter, from the area of this big quarter circle AOB, the area of this semicircle and the area of this small quarter circle PQS, in total you get the shaded area. So what is the area of the big quarter circle AOB? Because of the fact that the radius of the big quarter circle AOB is 10, the area of the big quarter circle AOB must be equal to pi times r squared, that is 10 squared over 4. So in total, the area of the big quarter circle AOB equals to pi times 10 squared over 4, minus the area of this semicircle. The radius of this semicircle is 5, and therefore the area of the semicircle must be equal to pi times the radius squared, that is to say 5 squared over 2, minus the area of this small quarter circle PQS. The area of this small quarter circle PQS must be equal to pi times x squared. X is 5, so it is pi times 5 squared over 4. So the area of the small quarter circle PQS equals to pi times 5 squared over 4. So here we have 10 squared is 100, so in total in the numerator we have 100 pi over 4. Here we have 25 pi over 2. We multiply both the numerator and the denominator by 2 in order to find factor of the other two expressions. 25 pi times 2 is 55. 25 pi times 2 is 50 pi, and 2 times 2 is 4. So in total, after we multiply the denominator of this expression by 2, we found out that it is equals to 50 pi over 4. And we have also minus 25 pi over 4. Here we took 4 as a common factor of those three expressions, so in total the denominator we have 4, and here we have 100 pi minus 50 pi is 50 pi, and 50 pi minus 25 pi is 25 pi. So in total we found out that the area that we are looking for, that is the size of this shaded region, in total it is equal to either 25 pi over 4 square inches in size, or in terms of numbers, the area of this shaded region is equal to 19.635 square inches in size. So we finished to answer on the first question. In the next step, I repeat on the solution of the second question. In the second question, our test was to find out the area of this shaded region. So in the drawing, we have two semicircles that intersect with each other at those 2 points M and B. Note that the diameter AB of this semicircle equals to 5. We define the radius, the center of this semicircle, this point is 0.0. So the radius must be equal to the diameter that is 5 over 2. The radius OA must be also equal to 5 over 2. In the next step, we divided the drawing here into 3 parts. The first part, we define this is the first part, that is the area that we are looking for. We define the size of this area that is the shaded region as A. This is to say, the area of this shaded region is equal to A squared in size. We define the size of this shape as B. That is to say, it is equal to B squared in size according to our definition. And finally, we define the size of this shape AMB as C. This is to say it is equal to C coincident size according to our definition. Because of the fact that those two semicircles can go into each other, they must have also the same areas. That is to say, the area of semicircle AB must be equal to the area of semicircle CB. What is the area of this semicircle AB? This semicircle AB consists of those two shapes. Therefore, the area of semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. The area of this first shape is C, the area of this second shape is B. So in total, the sum of the areas of those two shapes is equal to B plus C. So in total, if you found out that the area of this semicircle AB equals to B plus C units in its length. B plus C squares unit in its size. And the area of semicircle AB equals to the area of semicircle CB equals, they can go into each other. What is the area of the semicircle CB? Semicircle CB consists of those two shapes. And therefore, the area of semicircle AB must be equal to the sum of the areas of those two shapes that it consists of. The area of this first shape is B, the area of this second shape, that is the area that we're looking for, that is equals to A. So in total, the area of this semicircle CB must be equal to A plus B squared inside. So we all know that the area of semicircle CB equals to A plus B squared inside. So in total, according to equation 1, we found out that B plus C equals to A plus B. If subtract B from this equation, so B will get cancelled, and we left only if C equals to A. So those two areas, they are equal to each other in their sizes. That is to say, the size of this shaded area, it is equal to the size of this shape A and B. So in order to find out the size of this shaded area, we must have to find out the size of this shape A and B, and because of the fact that those two sizes are equal to each other. They are equal to each other. Therefore, the area of this shaded region must be equal to the area of this shape A and B because they are equal to each other in their sizes. A equals to C. So in the next step, we join points A and M together by straight line. By joining points A and M, we created peripheral angle A and B. Peripheral angle A and B subtend on chord AB. Chord AB is the diameter of this semicircle. And therefore, we know that according to rule 7, any peripheral angle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in size. Therefore, according to rule 7, peripheral angle A and B is equal to 90 degrees in size. In the next step, from point M, we do perpendicular on AB. Again, from point M, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M and AB. This point is point Z. We define the length of perpendicular Z as H. Then I copied the right triangle A and B in a new page, and analyze this right triangle A and B. AB is the diameter of this semicircle that is equals to 5 according to what is given in the question. Actually, this is the right triangle A and B that are coming from the original drawing. Again, AB equals to 5. MZ that equals to H is the height to the base AB because it rests 90 degrees with the base AB. In the next step, we calculated the area of this right triangle A and B using two different methods. And then we created equation 1 that says that the area of triangle AB according to the first method of calculation must be equal to the area of triangle this triangle AB according to the second method of calculation. The area of this right triangle AB according to the first method of calculation equals to the base AB times the height to the base H over 2. And again, the area of this right triangle AB according to the first method of calculation equals to the base AB times the height H over 2. And it must be equal to the area of this triangle AB according to the second method of calculation. The area of the right triangle AB according to the second method of calculation equals to the base AM times the height MB over 2. So here we have 2 on both sides of the question, so 2 will get cancelled, and we left only if AB times H equals to AM times MB. AB equals to 5, so we substitute AB by 5, and we find in total the size of the equation we have 5H equals to AM times MB. Again, according to equation 1, which we found out that 5H equals to AM times MB. In the next step, I copied again this triangle A and B in a new page and continue to analyze this right triangle A and B. So actually this is the right angle A and B. This is according to the original drawing. This right angle A and B, sinus 15 degrees equals to AM over AB. So sinus 15 degrees equals to AM over AB. AB is 5, so substitute AB by 5. So in total, we found out that sinus 15 degrees equals to AM over 5. If we multiply this equation by 5 and found out that AM equals to 5 times sinus 15 degrees. Likewise, in this right angle A and B, cosine 15 degrees equals to MB over AB. MB over AB. So it is MB over AB. AB is 5, so total cosine 15 degrees equals to MB over 5. If we multiply this equation by 5 and found out that MB equals to 5 times cosine 15 degrees. So in total, we found out that MB equals to 5 times cosine 15 degrees, while AM equals to 5 times sinus 15 degrees. So we have here equation 1 that says that 5H equals to AM times MB. Therefore, we can substitute AM in this equation 1 by 5 times sinus 15 degrees, and we substitute MB in this equation 1 by 5 times cosine 15 degrees. We did it, and we found out that in total 5H equals to 5 times sinus 15 degrees times 5 times cosine 15 degrees. Here we divide this equation 1 by 5. 5H over 5 is H. And here we have 5 times 5, that is 25, and 25 over 5 is 5. So on this side of the equation, we have to only find 5. So in total, according to equation 1, we found out that H equals to 5 times sinus 15 degrees times cosine 15 degrees. We use the trigonometric identity that says that sinus 2A equals to 2 sine A cosine A. Here we divided this trigonometric identity by 2 and found out that sinus 2A over 2 equals to sine A cosine A. We use this trigonometric identity in order to find out the value of sinus 15 degrees times cosine 15 degrees. So in total, according to equation 1, we found out that 5H equals to 5 times sinus 15 degrees times cosine 15 degrees. According to this trigonometric identity, we get that sinus 15 degrees times cosine 15 degrees equals to sinus 2 times 15 degrees over 2. Sinus 2 times 15 degrees is 30 degrees over 2. So in total, it is equals to sinus 30 degrees over 2. Again, sinus 15 degrees times cosine 15 degrees, in total, it is equals to sinus 30 degrees over 2 according to this trigonometric identity. So, according to this trigonometric identity. So in total, according to equation 1, we should found out that H equals to 5 times sinus 30 degrees over 2. So H equals to, here we have 5 over 2 times sinus 30 degrees. Sinus 30 degrees is 1 half. So in total, we should found out that H equals to 5 half times 1 half. So in the numerator we have 5 times 1, that is 5, over 2 times 2, that is 4. So in total, we should found out that the height H equals to 5 quarters. So here 8 mz is equals to 8 is equals to 5 quarters units in its length. Again, our task is to find out the size of this shaded area. Because of the fact that those two areas are equal to each other, and the size, that is to say, A equals to C, we just have to find out the area of this shape, A and B. But first of all, we join points M and O together by a straight line. By joining points M and O, we get the center angle AOM. The center angle AOM subtend on called AM. Likewise, we have angle ABM that subtend on the same chord called AM. And because of the fact that those two angles are both subtend on called AM, the size of this center angle AOM must be equal to 2 times the size of this angle ABM, because they are both subtend on the same chord called AM. The size of this angle ABM is 15, and therefore the size of this center angle must be equal to 15 times 2, that is 30 degrees. So according to rule 15, angle AOM is equal to 30 degrees in its size. So we have to find out the size of this shape A and B. This will be also the size of this shaded area, because those two shapes are equal to each other and their sizes. Shape A and B consists of two smaller shapes. It consists of this sector AOM, and it also consists of this side MOB. Therefore, in total, the size of the shaded region must be equal to the size of this sector AOM plus the size of this side MOB. Okay, so what is a sector? A sector is a portion of a circle. The green shape A or B is a sector. It is like a slice of a pizza. So it is a portion of a circle enclosed by two radii and RKB between them. The two legs, the two radii define also the legs of the sector. And the area of this sector A or B equals to the area of the circle that contains the sector, that is pi r squared, times the angle between the legs of the sector, that is theta, over 360 degrees. But again, a sector is a portion of a circle enclosed by two radii and RKB between them. And the area of this sector A or B equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is theta, over 360 degrees. We use this new formula in order to find out the size of this sector A or M. First of all, the size of this shape, those two shapes are equal to each other, their sizes. But this shape consists of those two smaller shapes. So this shape in total equals to the area of this first shape, that is the area of this sector A or M, plus the area of this triangle M or B. And then again, those two shapes are equal to each other and their sizes. And therefore, the size of this shaded region equals to the size of this shape A and B. But this shape A and B consists of those two smaller shapes. Therefore, in total, the size of this shape must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of this sector A or M plus the area of this triangle M or B. And again, in total, the size of the shaded region equals to the size of sector A M O plus the size of this triangle B O M, because shape A and B consists of those two shapes, two small shapes, and therefore the size of this big shape A and B must be equal to the sum of the areas of those two shapes that it consists of. So in total, the big shape A and B consists of the first shape, that is sector A M O, so that is the area sector A M O plus the area of the second shape that it consists of, that is actually triangle M O B. What is the area of the sector A or M according to the formula that I presented to you? It must be equal to the area of the circle that contains the sector, that is pi r squared, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Okay, then in total, the area of sector M O equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. Plus the area of the second shape that shape A and B consists of, this is actually the area of this triangle M O B. The area of this triangle M O B equals to the base BO times the height of the base MZ, that is edge over 2. So it is BO times edge over 2. So the area of the second shape that shape A and B consists of is the area of triangle M O B. The area of triangle M O B equals to the base BO times the height of the base edge over 2. So here we have pi r squared. R is 5 halves, therefore r squared is 5 r squared. So in total, pi r squared is pi times 5 r squared, and 30 degrees over 360 degrees is 1 over 12. BO is the radius of this semicircle, that is 5 halves. Edge is 5 quarters over 2. Again, BO is 5 halves, edge is 5 quarters divided by 2. Here we have 5 quarters squared is 5 squared, that is 25, over 2 squared, that is 4. So in total, this expression equals to 25 pi over 4, and we have to divide it also by 12. Here we have 5 times 5 is 25, 2 times 2 is 4, and 4 times 4 is 16. So in total, this expression equals to 25 over 16. So in total, this expression equals to 25 over 4 times 12, that is 48. So in total, this expression equals to 25 pi over 48 plus 25 over 16. So in total, we should found out that the area of this shaded region, that is the area that we are looking for this expression, is equal to either 25 pi over 48 plus 25 over 16 squared in its size. Or in terms of numbers, the area of this shaded region is equal to 3.2 squared in its size. Okay, thank you very much.